Right. Hi, everyone. This is the video for Chapter 9, Lecture 2. So we're going to finish the chapter with this lecture today. As you guys remember, last time we went over electron configuration using the easy electronic configuration guide, right? Dividing it into blocks and then using the period numbers as your principal quantum number. And then you don't have to memorize anything, right? Then we went over some irregular electron configurations, some exceptions. Remember, it's group 6 and group 11 that have exceptions where the one electron moves from the s orbital to the d. Okay, let's move on. Categorizing the electrons. Okay, so the inner core electrons are the ones that are in common with the previous noble gas. So you know how when you do short electron configuration, we do brackets, noble gas. Those are considered the core electrons. They're the innermost electrons, and they don't do anything. They're very boring. They do not participate in bonding, right? They're just kind of there. Then you have what's called the outer electrons. The outer electrons are the outermost electrons, and you can identify those by looking at the highest principal quantum number. So however many electrons are in that highest n number, the number in front, those are going to be your outer electrons. Okay, then there's the valence electrons. These are really important because these electrons are the ones that are involved in bonding. They're the most interesting electrons, really the ones that we care about the most when it comes to chemistry, right? Doing reactions and tracking electron exchange. It's of the valence electrons. So to figure out the valence electrons, all you need to do is look up at the group number, right? So what is the group number on the periodic table? Look at the column number. That tells you how many valence electrons for that atom. So what that means is that valence electrons are counting the outermost electrons, but also the electrons that are in orbitals that are not filled yet. So for example, in the transition elements, those d electrons get counted as valence electrons as well because the electrons, the d sublevel has not been filled yet. Okay, but again, really easy way to look at valence electrons, just look at the group number. All right, so let's look at the properties of things based on their electron configuration. The properties of elements are going to be dictated by that, the electron configuration. So let's look at, say, the noble gas configuration. Right, we're interested in this because it's really stable. That's what chemists have noticed, is that all the noble gases, they don't react very much, particularly the small ones. We do see limited reactivity with the larger noble gases, but in general, that's why they're called noble gases. Noble meaning unreactive. So you have the configuration of a noble gas is very desirable. And that's what we've been saying, right? We've been saying when things react, they want to have the same noble gas configuration, right? So things that are, closer to the noble gas want to gain electrons. And if they're at the other end of the table, then they're going to want to lose electrons, right? To get to the noble gas configuration. So why is the noble gas configuration so stable and that everything wants to be like it? Well, remember that rule that we had, or a pattern that we kept seeing, which is when electrons are paired up and when all the orbitals are filled, fully filled or half filled, they're unusually stable. So look at the noble gas configuration. We have NS2 P6. You guys see that? NS2 NP6. N just means the principal quantum number, right? But the S2P6 is the important one. S2 is a fully filled S sublevel, and 6 is a fully filled P sublevel, right? Why? Because P has PX, PY, and PZ, right? So S2P6, right? Or a total of 8 valence electrons, okay? And everybody's paired up, so it's very, very stable. If you look at the alkali metals, now we can explain why the alkali metals are so reactive. The configuration is NS1, right? So 2s1, 3s1. So S1, meaning you have one valence electron, And so alkali metals like to lose that one valence electron to get to a noble gas configuration of S2P6, right? And so that's why the alkali metals typically will form a 1+ charge when they're doing chemistry, right? Makes sense, right? Okay, let's take a look at the halogens. The halogens are in group 7A. So what is the quickest way to the noble gas? Well, you're gonna want to go to the right, which means gain an electron, right? So 2s2, 2p5, 3s2, 3p5, right? So ns2, np5 is the configuration. So if you add one electron, you become ns2, np6, just like the noble gas, right? And so that's why the halogens tend to have a 1- charge when they're doing chemistry, right? So you can kind of see that pattern. You can kind of, extrapolate to other groups too. So if you're at group 2A, then you're going to want to lose 2 electrons and become 2+, right? Or if you're group 6A, then you're 2 spaces away to the left of the noble gas. So you're going to gain 2 electrons to become 2-. So that's why we can predict a lot of the charges of these elements based on where they are on the periodic table, right? Because now we know that everything wants to be fully filled and be like the noble gas. So these are all of the elements where we can predict their charges, right? Group 1A, group 2A, 1+ and 2+, group 7A and group 6A, 1- and then 2-. And even group 5A, to a certain extent, you can predict nitrogen, right? Nitrogen is 3 to the left of the noble gas, right? So it's going to want to gain 3 electrons to get to the noble gas electron configuration. And then group 3A, right? What is the quickest way to the noble gas? If you're aluminum, say, well, it's going to be to the left, right? And so that's why aluminum is 3+. So as you can see, what quantum mechanics did for chemistry here, right? Before chemists knew that this would they saw the pattern, but they couldn't explain why. Okay. So they knew that group 1A tend to be 1+, group 2A tend to be 2+, but they couldn't explain why. Right. Quantum mechanics gave them the insight to, okay, it's because now we got, things called orbitals, and there are only 2 electrons in each orbital, and if they pair up, they kind of reduce their potential energy. They become more stable, right? So fully filled shells are more stable than, say, half-filled shells or, oddly filled shells. So that's why you have these patterns, right? Now we can explain the why. Okay, let's go to the electron configurations of ions. So, we did easy electron configuration with the neutral atoms. What about the ions? Pretty easy. You can do it one of 2 ways. Okay, you can do the neutral configuration first. So, for example, sulfur would be 1s2, 2s2, 2p6, 3s2, 3p4. And then what if, you want to do electron configuration for the sulfur anion? Well, sulfur is in what? Group 6A, right? So what charge would it be when it does undergo reactions? It's going to be 2-. 2- means a gain of 2 electrons. So where are you going to put it? Well, you're not going to put it in 3s. You're not going to put it in 2p, right? Those are full. There's only one place where it's not full. That's the 3p sublevel. So you add 2 electrons to here and it becomes 3p6, right? And whose electron configuration is that, right? Why did it want to gain 2 electrons? That's got to be the noble gas. And which one? Let's see. That's neon and that argon, right? S2- is now argon's electron configuration. And that's why it wants to beat that, because it is more stable. If you go to magnesium, okay, now look at your periodic table. Magnesium is in group 2A. You can just do the neutral first, 1s2, 2s2, 2p6, 3s2, and then you realize, okay, what is the outermost electrons? Is in the 3s. If I get rid of those 2, I'm back at neon, right? I'm back at 1s2, 2s2, 2p6. So that's why magnesium wants to be 2+, right? It's in group 2A. It makes sense to lose all of its valence electrons and become like the noble gas. Okay. Now you don't have to, do the configuration of the neutral first. You can just straight up with your finger put it on the periodic table, right? At the magnesium spot, And if it's 2 plus, then you want to walk back 2 steps, right? And you see, oh, I'm at neon's configuration. So it's got to be 1s2, 2s2, 2p6, right? Okay, so the next thing we're going to do is we're going to use our knowledge of all of this, right? Where electrons are kind of mapped out in the atom to explain some periodic trends that, early scientists have been seeing, but couldn't explain until quantum mechanics, right? So before we get into trends of atomic radius, let's define what a radius is first. So we got 2 types of radius, a van der Waals radius and a covalent radius. So van der Waals radius is for like a non-bonding type radius. You have, let's say, a bunch of krypton atoms stacked on top of each other. The van der Waals radius is taking, the distance between 2 nuclei and divide by 2, right? And covalent radius, you're gonna do the same thing as well, because as you can see, the covalent radius is tricky because there's no border for the radius, right? So the most accurate way is just taking the distance between 2 nuclei and then divide by 2. Right. Either way, though, what a radius does for us is tells us how large an atom is, right? And so, yeah, let's look at the trend for that. So the atomic radius, what we've noticed is that it decreases across a period. So if you look at this graph here, okay, so it's a little busy, so let me explain it to you. Notice that the red and the blue, okay, those are the columns, okay, and then these are periods here, okay. So here's our period 2, right, lithium to neon, and then period 3, sodium to argon. Okay, here's period 1, hydrogen and helium, right? So what do we notice with atomic radius is that it decreases as you go across a period for the main group. Remember what the main groups are? The wings of the periodic table, and skip the transition metal, right? Because the transition metal, it bucks that trend. Okay, so let's just ignore that for now. We're just talking about the main group. So as you go across the period, you're going to have a decrease in size. Okay, so we can ask, why is it like that, right? Oh, and then atomic radius increases as you go down a group. Okay, so you can see that from lithium to cesium here, right? You have an increase in atomic radius, and from helium to xenon, you have an increase in radius. And this makes sense because, when you go down a group, you're basically putting on a new layer. Okay, that's how you can think of it. So you're putting on a new, like the atoms get further, the orbitals get further away from the nucleus, right? And so, of course, you're going to have a larger atom. Okay? Now, why is it that the atomic radius decreases as you go across the period? This is because as you go across the period, you add 1 proton and 1 electron, right? As you go from left to right, you add 1 proton and 1 electron. So, you would think, oh, wait, well, then my atom size should stay the same. However, the adding of the 1 proton is more important than the adding of the 1 electron. So you adding the 1 proton allows a bigger effective nuclear charge to draw in the rest of the electrons. So that one addition of the proton kind of pulls all the electrons closer to it. And so the valence shell is going to be held closer. And so therefore, that's why your atomic radius will decrease as you go across. Right. Now you can actually see some numbers here, right? So ignore the yellow because that's the transition metal. So we'll explain later to why it does this. But for now, you're just going to concentrate on the blue and the pink. And clearly, you see the trend there, right? The radius decreases as you go across and increases as you go up. These numbers are in picometers. And remember what picometers are. It's times 10 to the negative 12 meters, right? Okay, so that's all, what you guys should know as far as testing goes. If I ask which one's larger, lithium or beryllium, you guys say lithium, right? Because lithium is to the left of beryllium. So know your trends, but then also know why, right? So as you go across the period, it's because the effective nuclear charge increases, pulling all the electrons closer towards it, right? Whereas when you go down, what happens is you're basically putting on another jacket. Just think of putting on another layer because you're increasing the quantum number as you go down group, right? And so of course you're gonna be bigger, right? You're adding another shell. Okay, so let's talk about the transition metals. Okay, so here are the transition metals, as you can see, it goes down a little bit, but then it goes back up. You see that? It goes from 162 down to about 125, 123 here, and then it actually goes back up. So the transition metals have a different trend than the main group because remember how the electron configuration goes. The N-1d shell is being filled, right? So if you're in period 4, then the 3d shell is being filled. And remember how shielding works. Inner electrons shield much better than electrons in the same energy level. So as you go through the transition metals, what you're doing is you're putting electrons into an inner orbital. And as you're doing that, the Z effective gets lessened. So then the outer electrons, the valence electrons, are not held as tightly by the nucleus. So the atom actually gets bigger later, right? As you fill in more and more electrons. So in the later part of the transition metals, you see that the size actually goes up, okay? And so that's how the shielding works, right? This is the picture here. If you have this valence electron out here, and you keep adding electrons in between that outer electron and the nucleus, what you do is you lessen the Z effective. And so that nucleus can't hold on to the outer electron as tightly. And that's what makes an atom size get bigger, okay? So shielding causes atom size to get larger, okay? And the Z effective, right, how effective the nucleus is at attracting is what makes atoms get smaller, okay? So again, when you look at the transition metals, right, at first, when you're like, let's say you're at scandium and this would be 3D1, 3D2, right, second electron, third electron, fourth electron. At first, it goes down because the Z effective is winning, right, just like the main group trend. But then as you fill more and more of the inner electrons, now the Z effective lessens, right? Because these electrons start to shield the outer electrons. And so then the atom balloons back up, right? So that's really interesting. Okay, let's talk about the electron configuration of cations now. All right, we did it for anions earlier. So let's look at aluminum, the neutral electron configuration. Aluminum neutral is 1s2, 2s2, 2p6, 3s2, 3p1, right? But the ion, remember, aluminum is in group 3a, so it's going to want to lose 3 electrons. Where is it going to come out of first? Well, we can think about it. Where is it easier to steal an electron? From the inside or the outer electrons? Well, obviously, the outer electrons are going to be held less tightly by the nucleus, right? So those electrons are going to get lost first. So what you're going to get, you end up getting is 1s2, 2s2, 2p6, right? The 3 electrons coming out of the 3p and the 3s orbital, right? Which are the outermost, okay? So then aluminum 3 plus, as you can see, has the same electron configuration as who? Neon, right? And you have fully filled, everybody's paired up in the S and the P sublevel. So you have a very stable configuration, right? Let's look at the electron configuration for transition metals. Okay, so pay attention closely here. Everybody always gets it in the lecture, but then forgets about it on the exam. Okay, so don't let this be you. It's actually really makes perfect sense why it works this way, but everybody forgets, okay? So if you look at the iron atom, the neutral version, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, and now you think about what would be iron 2 plus configuration is. So now you have to decide, where do the 2 electrons come out of? Which of these sublevels are going to come out of? Well, again, same reasoning, right? It's gonna come out of the outermost electrons, right? And where are the outermost electron? Where the n number is the largest. So where's n the largest? 4, right? So the transition elements they're filling inner electrons, right? Inner orbital electrons. So you don't touch those. You're gonna take it out of the 4s first before you touch the 3d. Okay. So if you lose 2 electrons, it's gonna come out of 4s, and all you have is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. Okay. So no more s. Okay. If it's an iron 3 plus, then you're gonna take 3 electrons out of that configuration. Well, where's it gonna come out first? Again, 2 of them is gonna come out of the 4s first, and then 1 more from the 3D, because that's going to be the next highest, right? After the 4s, the 3D is the furthest from the nucleus. So you take 1 more out, and so what you get is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Okay. And let me show you real quick, like how you do this quickly so that you don't have to do the neutral configuration first. So get your periodic table, everybody. Okay. If I say, okay, what is the configuration for iron 2 plus? Put your finger on iron, walk back until you see the previous noble gas, which is brackets argon, right? And then walk forward and go, okay, where am I in the orbital? It's going to be 3D, right? Okay, so now put your finger on iron again, walk back 2 spaces, and what is that? What is that group number? It's going to be 6. And you're like, I'm in period 4, so I'm going to drop it down to 3 because I'm in the D block, so 3d6. Okay, let's do it for iron 3 plus. Okay, so previous double gas, again, it's argon. Okay, then I'm going to put my finger on iron. I'll walk back 3 spaces and look up at the group number. The group number is 5. And what block am I in? I'm in the D block. Here it is 4, so drop it down by 1, 3d5. Easy, right? So that's all you got to do. So notice there are no s electrons in transition metal ion electron configuration. Okay, there are no s electrons in transition metal ion electron configuration because it gets lost out of the s orbital first. That's the outermost one. Okay. All right, let's do a couple more examples of that. So let's say if I ask you, what is the configuration for technetium 4 plus? Okay, so you're like, okay, technetium, that's TC. I'm gonna walk back and see that, oh, okay, previous double gas was krypton. Okay, and then I need to walk back 4 spaces from technetium, so that's gonna be group 4. So that's 4, right? And that's D4. And then what period am I in for technetium? 5. So, but I should drop it down to 4, right? Drop it down by 1 to 4. So krypton 44, right? Pretty easy. Let's do silver plus. Okay. Again, brackets krypton for silver. Put your finger on silver and just walk left 1 space. And now you're in group 10. Okay. So, and you're in period 5. So it's 4D 10. Okay. Alrighty. Okay, so the next thing you want to learn is the terms for how many unpaired electrons you see in your electron configuration. So if you see one unpaired electron, just one, then we say this is paramagnetic. We say this compound or this ion is paramagnetic. Paramagnetic means it will be attracted to an external magnetic field because you have unpaired electrons. Remember, unpaired electrons spin on their axis, and as they spin, they create their own little small magnetic field. So that small magnetic field can be influenced by a larger external magnetic field. Okay, so that's what we call paramagnetism. Okay, so as long as it has one unpaired electron, it's considered paramagnetic. Okay, if it has no unpaired electrons, meaning all the electrons are paired, then we have what's called diamagnetism. Okay, and it will have there's no effect. It'll actually be slightly repelled by an external magnetic field because it has no more spin, right? All the spins are paired up. Okay, so let's put what we just learned to the test with some example problems. So let's do these together. Which atom has the larger atomic radius? So get out your periodic table. All right, we have carbon or fluorine. Which one is larger? Well, isn't fluorine to the right of carbon, right? So carbon is going to be larger. Okay. Okay, next we have carbon or germanium. Okay, so germanium is below carbon, right? Remember, atomic radius increases as you go down the groups. You're going to pick germanium. Right. Then we got nitrogen or aluminum. Okay, well, that's easy. Nitrogen's in period 2. Aluminum is in period 3. So it's going to be nitrogen. And also nitrogen is to the right of aluminum, right? So, oh, sorry. So that's going to be smaller. We want to pick the bigger one, actually. So it should be aluminum, okay? Not this one. That one's larger. And then aluminum and germanium. Okay, so at this point, you see, yeah, so germanium is below aluminum, but aluminum's to the left. So you can say you can't decide, right? There's cases where it's close, so unable to tell would just be a good answer here. All right. Okay, let's keep going. Okay, so tin or iodine. So we look at tin. It's tin to the left of iodine, so it's going to be tin, right? It's going across. Remember, size decreases as you go across. Then germanium and polonium. Germanium, polonium. Okay, so germanium is to the left of polonium, but polonium is 2 spaces down, so 2 periods down. So you guys, anytime that you're going down a group, that effect is actually gonna be higher, especially if it's going 2 groups down. So I'm gonna say polonium. Okay. Chromium and tungsten, obviously tungsten, because tungsten is below, right? As you go down the group, you have an increase in atomic radius. Then we got fluorine and selenium. It's gonna be selenium, obviously, because selenium is to the left and below fluorine. Okay. All right. So obviously, you want to know your trends so that you'd maybe be able to answer those questions. Okay, let's do this one too. Arrange these elements in decreasing radius. So whenever you get a problem like this, what I want to, try and do is get the ends first, right? Get the smallest and the largest first, and then fill all the rest in between. So this is kind of like how you're gonna have it on the next exam. I'm gonna give you, just several elements, and then you're gonna do the ordering. Now decreasing radius means you're going from biggest to smallest. So make sure you're using the greater than sign. And so, okay, let's figure it out. Which one is gonna be the biggest and the smallest, and then we fill the rest in between. So we have sulfur, calcium, fluorine, rubidium, and silicon. All right, so biggest, I know the biggest elements are going to be to the left and down, okay? So that's going to be rubidium. I know it's going to be here. And then the smallest is going to be up and to the right. That looks like fluorine, right? So we're doing decreasing, so rubidium first, and then fluorine, right? Biggest to smallest, greater than sign. So now we got that knocked out, okay? I'm gonna go with which one's the next biggest, right? Just keep playing that game, and it makes it easier to rank. Calcium's gonna be the next biggest. And then between silicon and sulfur, it's silicon. Right? So that's how it's gonna look. Rubidium greater than calcium, greater than silicon. So that's exactly how you should do it. Make sure you know what decreasing and increasing means, right? This is decreasing because you're going from largest to smallest. And use the greater than sign. If you're going from smallest to largest, then you use the less than sign, right? Smallest to largest. Okay. All right. Here, write the electron configuration and orbital diagram for each ion. Determine whether it is diamagnetic or paramagnetic. Okay, so it wants aluminum 3+ first. All right, I'm looking here at aluminum. Previous noble gases, brackets neon. It's okay, you can do short. Remember, short, you can use the short configuration as your default unless stated otherwise. If I wanted full configuration, it would tell you, right? So brackets neon is gonna be a 3+, right? 3+, so put your aluminum, figure on aluminum, walk back 3 spaces, you add neon. So for neon's configuration, it's actually brackets helium, 2s2, 2p6, right? So to draw the orbital diagram, I go brackets helium. How many boxes should you draw for 2s? Just one, right? There's only one type of s orbital. How many boxes should I draw for p? 3. So 2p. Put in 2 electrons here, 6 electrons here. 1, 2, 3. Remember Hund's rule, right? Fill in each first before you pair. Okay. So like that. And this is diamagnetic. How do we know? All the electrons are paired up. Okay. Okay. So that was A. For B, sulfur 2-. Okay. So I got sulfur, put my finger on it, walk forward 2 spaces, I'm at argon. Okay, so argon's configuration is previous noble gas, and then which is neon, and then 3s2, 3p6. Okay. So I'm gonna draw the orbital diagram again. 1 box for the 3s, 3 boxes for the 3p. 1, 2, 1, 2, 3, 4, 5, 6. Okay. Again, diamagnetic. Why? I don't have any unpaired electrons. C, iron 3+. Okay, remember how to do it? Previous noble gas for iron is brackets argon. Okay, from iron, walk back 3 spaces, and then look up at the group number. That's 5. And then figure out what block you're in. It's D. and period 4, so 3d 5. Okay. And then to draw the orbital diagram, how many boxes should I do for d orbital? Remember how many d orbitals there are? 5. So 5 boxes stuck to each other. Label it 3D and put 5. 1, 2, 3, 4, 5. Remember, don't be the creepy person on the bus, right? 1 in each box first before you pair. So are we diamagnetic or paramagnetic? Well, we have 5 unpaired electrons, right? Anytime you have any unpaired electron, it's going to be paramagnetic. Okay. Okay, let's do these ones as well. Do the electron configuration for cobalt 2+, N3-, and calcium 2+. Okay. So cobalt 3+, brackets. Previous noble gas for cobalt is argon. Okay, put your finger on cobalt, walk back 3 spaces. Oh, look at the group number. I'm at 6. That's D6, and then I'm in period 4, so drop it down 1, 3d6. How many boxes should I draw for D? 5, all stuck to each other. And then 6 electrons in there. So 1 in each box first, and then the 6th one gets paired in the first box, right? Remember that. All right, so we have paramagnetic or diamagnetic. Well, we have unpaired electrons here, so para. Next one, N3-. Okay, put my finger on nitrogen, walk forward 3 spaces. That's neon configuration, which is brackets helium, right? Always do your previous noble gas and then some. That's gonna be 2s2, 2p6. So 1 box for the S, 3 boxes for the P, 2 electrons, 6 electrons in the P. So everybody's paired up. Say it is diamagnetic. C, calcium 2+. Okay, put your finger on calcium. Walk back 2 spaces. Oh, you're at argon. Configuration of argon, which is brackets neon, 3s2, 3p6. 1 box for the 3s. 3 boxes for the 3p. Up and down for the 2 electrons. 1, 2, 3, 4, 5, 6. 1p. Right? And diamagnetic, because you have 0 unpaired electrons. Right, yeah, so make sure you can do that, right? Draw, do the ion configuration, and then also draw the orbital and say whether it is paramagnetic or diamagnetic. Okay, so now next up, trends in ionic radius. Okay, so we know that the neutral ones, right? Just the neutral atom, right? It increases as you go down and decreases as you go across. For the ionic radius, if you look at the cations, okay, do you see that they're so much smaller than the neutral version, right? And this is easy to see because easy to reason. When you lose electrons, now your Z effective is way bigger, right? The attracting power of the nucleus is way larger because now it only has to hold on to a fewer number of electrons, right? So it still has the same number of protons, but fewer electrons to hang on to. So cations are always so much smaller than neutral version, right? Because of the huge Z effective. And so you can see that here, right, with numbers. So these are all going to be in picometers. In a lot of instances, it's more than twice, right? The shrinkage, it's more than twice. So look at like, for example, gallium, right? Neutral gallium is about 3 times the size of gallium 3 plus. Okay. Look at beryllium, it's almost 4 times the difference, right? Between a neutral and the cation. Okay. But all, what you can see is always the cation is smaller than the neutral. Okay. Now with the anion, that's going to be opposite, right? When you have an anion, that means you added electrons, but you keep the number of protons the same. So now the nucleus has to work harder to pull all the electrons inward, and it can't, right? And so it gets larger, right? You're giving it too many electrons, right? So you didn't give more protons. The number of protons stay the same, but you add more electrons. So anions are always going to be larger than the neutral version. Makes sense, right? Okay, so let's do this example together. Choose the larger atom or ion from each pair. Okay. Sulfur or sulfur 2 minus. Okay, well, that's easy. Sulfur 2 minus is going to be larger, right? Because you have more electrons and the same number of protons. Between calcium and calcium 2 plus, calcium's larger, right? Okay, because the cations is always smaller. Okay. And then in Br minus and Kr. Okay. Pause the video right now and think about that for a second. Okay. A lot of people will think, okay, it's going to be the same size, okay? Because Br minus and krypton has the same number of electrons, right? Br minus has the same number of electrons. But you need to consider how many protons each have, right? So for bromine, you have 35 protons, okay? And right, for Br minus, let's label, we have 35 protons and 36 electrons, right? For krypton, what do we have? 36 protons and 36 electrons, right? So now it's pretty apparent which one is going to be larger. They have the same number of electrons, but krypton has more protons to pull those electrons in. So krypton's going to be smaller, right? For sure, right? So it makes a lot of sense. You can really reason this out, right? Just have that periodic table in front of you. Okay, let's keep going. Potassium or potassium plus, obviously. Potassium neutral. Fluorine or fluorine minus. It's going to be fluoride. And then we got calcium 2 plus and Cl minus. So kind of the same situation as we had before. They both have the same number of electrons, right? So calcium has, for calcium, it's 20 protons. And it lost 2, so it's at 18 electrons. Okay, and then Cl minus. Cl minus is at 17 protons. And it has 18 electrons. Okay, this is pretty obvious now, right? Calcium has way more protons, so it's going to be able to pull its electrons tighter. It's going to be smaller. So Cl minus is your answer, right? So, in certain cases like this where it's not obvious right away, right, I would suggest doing this. Just count, your number of protons and electrons. Then it's really easy to reason, right? Okay, so next up, the next trend we're going to do is called ionization energy. Okay. So let's define it first before we go through the trend. So ionization energy is the minimum energy needed to remove an electron from an atom or ion. Okay. So just like it sounds, right? Ionization means making an ion out of it. Okay. In this case, by taking an electron away. And you guys know that it would require energy, right? It's an endothermic process because you're trying to steal an electron from the nucleus. There's an attraction between the nucleus and the electron, and you're trying to steal it, right? So it's going to take energy to remove an electron. And the equation for it would be this, right? So let's say you have M, which is an element. You need to have plus, right, IE to get to M1 plus and 1 electron, okay? So what that means is you have to insert ionization energy to make M neutral become M1 plus and lose an electron, okay? Now, you can have successive ionization energy. So this one's called the first ionization energy. You can do it again, and it would be called the second ionization energy. So you take M1 plus, okay, add more energy, and all of a sudden you can rip another electron away and become M2 plus, right? So your atom is now dication, right? And you lose another electron. So it's pretty easy to reason as well that the successive ionization energies are going to increase, right? Because when you remove the first electron, what happens to the atomic size? It went, okay? So now you're trying to steal yet another electron from an atom that's even smaller, right? From an ion that's even smaller. Well, that's going to be even harder, right? So successive ionization energies are always going to increase. So here's how the trend goes. The first ionization energy will decrease down the group, and you can use size to reason this out, okay? So it's easier to steal an electron from a larger atom, right? Because the peripheral electrons are further away from the nucleus. It's less attracted to it. It's much harder to steal an electron from a smaller atom, okay? So use your trend, your atomic size trend, to reason out the first ionization energy trend, okay? So when you go down a group, your atom size gets larger. So your first ionization energy will decrease. Okay? But as you go across the period, the atomic size will decrease, right? And therefore ionization energy will generally increase across the period. Okay? So here's the graph for that, right? You can see that in the purple here, right, that's across the period. Lithium to neon, sodium to argon, okay, and potassium to krypton, okay? So across the period, you do see a general increase in ionization energy. And that even works for the transition metals, but it's a little bit less regular, right? Because remember, the size trend in the transition metals is kind of weird, right? It dips down first, but then it increases back up for atomic size. So that's why transition metals is looking a little, weird. But what else notice for each period, there is a little dip, right? There's a general increase, but then there's a dip. There are two dips here, right? So let's notice what atom that is and see if we can explain why there's a dip, right? So what's after lithium? It's beryllium, and after beryllium is boron. So between beryllium and boron, you see a dip in the ionization energy, and between nitrogen and oxygen, this one is nitrogen and oxygen, okay, there's also a dip. So let's explain that with electron configuration. Okay. That's the cool thing, is you can use electron configuration to explain so many things. So to explain why you see a dip, let's do a orbital diagram. Okay, you have, for beryllium, it's 2s2. Okay, brackets helium 2s2. For boron, it's brackets helium 2s2 2p1. So borons, even though boron is smaller than beryllium, it actually has a slightly lower ionization energy. Now we can see why, because if you take this electron away from boron, you get a really nice configuration, right? A fully filled orbital. Remember, that's always desired for some reason with these elements, right? Totally, everything totally paired up, right? A fully filled subshell. So if you take this electron away, you get a fully filled subshell. However, if you try to take this electron away from beryllium, you're screwing up a really nice configuration. And so that's why the first ionization energy of beryllium is actually higher than boron, even though beryllium is bigger, right? So interesting. So there was another one that did that, right? There was another instance that was between nitrogen and oxygen. So let's see that. So for nitrogen, it's brackets helium 2s2 2p3 1 2 3. For oxygen, it's brackets helium 2s2 2p4. Okay, you see the same thing again. If I take this last electron of oxygen, I get to this configuration where you have fully filled subshell and a half-filled subshell. That's a really nice configuration, right? But if I do that to nitrogen, I take this electron away, I screw up a really nice configuration. And so that's why nitrogen's ionization energy is higher, right? It's harder to take an electron from nitrogen than oxygen, even though nitrogen is larger. So you see this play out again in other periods as well, right? So not just period 2, but also in period 3, right? And to some extent, period 4 and 5 too, but not so much in period 5, right? So really, really interesting there. All right, so here's some numbers to it. As you can see, increasing ionization energy as you go to the right for the main group. Okay, why? Because atoms get smaller. And by the way, these units are kilojoules per mole, the numbers that you see here. Then when you go down a group, you have decreasing ionization energy. Why? Well, the atoms get larger, right? So it's easier to take the electrons away. Right. Oh, yeah. So this, we already explained this, why nitrogen's ionization energy is actually higher than oxygen's, right? Because if you take oxygen's electron away, it actually wants to give that electron away because it gets, it's easier because it gets to this nice configuration. Whereas for nitrogen, you take this electron away, you screw up a nice electron configuration, right? Okay, so trends in successive ionization energies. We already, gathered this earlier, right? We were like, the successive ionization energies should increase, right? Because every time you take an electron away, the atom size gets smaller. And so it's even harder to steal another electron. So if you look at sodium and magnesium's example here, you can see that, the first ionization energy is always the lowest, right? And then the third is always the highest, okay? But there's another thing that you see that is really interesting. For sodium, the second ionization energy is huge, right? You go from 496 to also 4,560. So to steal the second electron of sodium is 10 times harder. Okay, but it's not like that for magnesium. Okay, for magnesium, where is it really hard? It's the third ionization energy, right? So the first one is 700. Of course, the second one's gonna cost you about twice as much. Okay, but then the third one, why is it so high? Okay, so you gotta think about it. What is going on after sodium loses one electron? Look at the periodic table. It becomes neon's configuration, right? So when you take the third electron or second electron away from sodium, you're trying to steal a noble gases electron, basically. And so it's going to be super high, right? But for magnesium, since magnesium is in group 2A, then it's the third electron of magnesium that means, that you are pulling away. That's really hard because it has the noble gas configuration, right? So by using these numbers, successive ionization energy numbers, you can actually figure out what element we're talking about. So let's say, I tell you, okay, we are now in period 3, everybody, and I'm talking about an element that has a really high 5th ionization energy. Okay, a really high 5th ionization energy, like this one, for example, okay? So you can see the gap, right? Between the fourth and the fifth. The fifth one is really, really high. So that means that my element has to be in group 4. Group 4, period 3 is silicon. Okay. So, silicon, after it loses 3 electrons, okay, the fourth one is going to be really hard to take away because that is the one that has a noble gas configuration. Okay. Okay, let's try it again. I'm thinking of an element in period 3 that has a really high 7th ionization energy. Okay. That means that my element must be in group 6. Group 6, period 3 is sulfur. Okay. So you see here, the 7th ionization energy is really high, sulfur, right? Because after it's lost 5 electrons, the 6th one, it gets a noble gas configuration, right? And the 6th one you're trying to steal, sorry, for sulfur, it's in group 6. So after it's lost 6 electrons, it gets a noble gas configuration. And the 7th one you steal is gonna be of the noble gas, basically. And so that's why it's that jump, right? Okay, let's do some more practice problems on the basis of periodic turns. Determine which one has the higher first ionization energy. Okay, so aluminum is sulfur. Basically, we're trying to figure out which one's smaller. So sulfur is smaller, so it's gonna have higher first ionization energy, right? Arsenic or antimony, AS or SB. Well, arsenic is smaller, so it's gonna have a higher first ionization energy. We got nitrogen or silicon. Obviously nitrogen smaller, so yep. You see how I use size to do it, right? That's why it's kind of nice. If you just know size, you can reason everything else out. Okay, oxygen or chlorine. Oxygen is smaller. Well, hard to say because oxygen is on top, chlorine is at the bottom, but to the right. So for this one, you can say, I'm not sure. I put my bet on oxygen though, because going down a group is like, putting on a jacket. So yeah, it's kind of hard to say, but I would think oxygen. Yeah. Okay, let's keep going with this one. Tin or iodine, which one has the higher first ionization? It's gonna be iodine. Because iodine smaller, right? Again, going by size. Calcium or strontium? Strontium for sure, because it's smaller. Carbon or phosphorus? Okay, again, which one is smaller? Ooh, yeah. So that one's a little harder to tell because carbon is on top, but it's to the left. So again, you just say you can say I don't know, and that's fine, or can't determine, given this information. And then the last one, I think we can tell. Yep, it'll be fluorine. Fluorine and sulfur. It's fluorine's to the right and above. Okay. All right, let's do this part. Arrange the following in order of decreasing first ionization energy. So we're back to that one. Same elements as before, but we're just ranking it by decreasing ionization energy. And we have sulfur, calcium, fluorine, rubidium, and silicon. Okay. Remember that my strategy, do the largest and smallest first, right? It did say decreasing, so again, high ionization energy to small ionization energy. So high ionization energy would be a smallest atom, right? So it's gonna be fluorine. And lowest ionization energy would be the largest atom. So rubidium over there. And then you fill in between again, right? Again, it's gonna be greater than as your sign. Okay. calcium here, right? And fluorine here, I'm gonna say sulfur, and then silicon. Yeah, sulfur is smaller than silicon, so it's second. Okay, then silicon, calcium, and then rubidium. Okay. Decreasing ionization energy. Okay, the next trend. This next trend is the opposite of ionization energy. It's called electron affinity. So it's like how much you like the electron now, meaning giving the atom the electron, right? Ionization energy was the energy you need to take an electron away. Now you're gonna give the electron, get energy back. So it's exothermic, right? If one process is endothermic, the other one has to be exothermic. So giving the electron to the atom, right? Because the nucleus is attracting the electron. So that is a drop in potential energy. So you have an exothermic process. And therefore, all of your electron affinity numbers tend to be negative, right? Because it's exothermic. So the easy way to think about this is think in terms of metals and non-metals. Do metals like electrons? No, they like to lose them, remember? But non-metals do, okay? So things that have high electron affinities would be metals, non-metals, right? And things that are with low electron affinity would be metals. So the more negative the number, the larger the electron affinity, okay? So electron affinity doesn't have a regular trend, so it just has a very, very general trend, okay? Very general. So that means when I ask you a question on quiz or exam, I'm gonna make it abundantly clear, okay? I'm not gonna be tricky about it, okay? So if you know your trend, you can get the answer right, okay? So here's how it looks, right? You can see that the nonmetals, right, have a higher electron affinity, a greater negative number, right, because it's exothermic, than the metals, right? And even some of the metals have a positive electron affinity. You're like, what? I'm supposed to get energy back, right? But actually, no, I have to actually pay you energy to give you the electron. And that's crazy. So it's the same for the noble gas, right? Because the noble gas configuration is so perfect, it does not want an electron to screw it up, right? So it does not want electron at all, right? So its electron affinity is actually in the positive. Okay, so you can say like this. Generally, when you go across the period, electron affinity will increase, okay? And generally, when you go down a group, electron affinity will decrease, right? And you can kind of see that with the numbers here, but you can also see how it's not very regular, right? So as I'm saying, I will make it abundantly clear, okay? Like I'll be like, which one has higher electron affinity? Fluorine or silicon, right? There's just really no question there. Fluorine is going to have a higher electron affinity. Okay. Now the last trend we're going to go through is called metallic character. Okay. So metallic character is how closely an element's properties match the ideal properties of a metal. So, you know, that's how we divide the periodic table, right? Into metals and non-metals. And then, of course, there's a bunch of stuff in between. So that's what we're saying. How close is that element to the ideal properties of a metal? And that's high metallic character, okay? Whereas opposed to non-metals has low metallic character. So what are the ideal properties of metals? Here they are. Metals are malleable, they're ductile, they're shiny, lustrous, they conduct heat and electricity really well. They form cations in solutions, right? They like to lose electrons, and therefore, what do we call that? Oxidized. Metals like to be oxidized. Non-metals, on the other hand, are brittle, dull, not reflective, not shiny. They're more insulators. They form anions and polyatomic anions, and they like to gain electrons in reactions, so therefore they like to get reduced. Okay. So those are the ideal, right? So metallic character, then, of course, it's going to decrease as you go across the period, right? Because to the right are the nonmetals. So metallic character is going to decrease as you go to the right, but it's going to increase as you go down. Okay. So that's the last trend for this chapter that you should know. Okay, it's just very general. Metallic character decreases as you go across and increases as you go down. All right, so let's do this together. Oh, ignore that. That should be metallic character, but it wants it what? Higher metallic character. So which one's gonna have higher metallic character? Tin or tellurium? We're gonna say tin, because it's to the left, right? Anything to the left and down is higher metallic character, right? P or SB? SB, because SB is below P. GE or indium? Germanium name is going to be indium. I would say indium, yep, because it's below and to the left. And then sulfur or bromine. This one's a little harder again, right? Because sulfur is above, but it's to the left. So you can say for D, you can't tell. Okay, that's which is fine. Okay, let's keep going. Germanium or tin. You'd say tin. Right, tin is below germanium. Gallium or tin, more metallic. Okay, so again, you may not be able to tell here because gallium is to the left, but tin is down. Okay. Okay, phosphorus or bismuth. Bismuth, because bismuth is below. And then boron or nitrogen. Boron, obviously, because boron's to the left. Right. And this one. All right. So increasing metallic character. Right. The atoms first. Silicon, Cl, sodium, and rubidium. Okay. There's definitely a method to this. When you're doing metallic character and it wants it in increasing metallic character, so lowest metallic character to highest metallic character, first divide it into metals and non-metals. Okay. Otherwise, it's really confusing. Right? Divide into metals and non-metals. So I got sodium and rubidiums are metals, and these are non-metals, more or less. Right? So I rank the metals and then I rank the non-metals separately, and it just makes my life easy. Right? So remember doing increasing metallic character. So lowest metallic character first must be my non-metals. But which one's the lowest between silicon and chlorine? It's gonna be fluorine, right? And then less than sign, right? Then silicon. And which one's highest metallic character? That's looking like my rubidium, right? And then comes sodium next. Okay. So that's the strategy. All right. So that's it for this chapter. Yeah, that's it. So I'll see you guys next time for chapter 10.